All right, welcome to Chapter 3, Probability Topics. So this chapter is a little, probably one of the more difficult of all the chapters in this entire semester, so I definitely recommend listening to this lecture more than once and making sure especially that you understand the terminology and when to use each certain equation. Okay, so here we go. Speaking of that, terminology. So, number one, probability. That's the big thing we're going to talk about in this chapter here. So, probability is a measure that is associated with how certain we are of outcomes of a particular experiment or activity. Right? So, a good example of that, if you've ever collected sports cards or Pokemon or Magic cards, anything like that, they come in packs, right? They're wrapped up in packs, and if you read the back of the pack, it'll tell you the probability or the odds of pulling any certain special card, right? So one thing to know, especially if you've opened packs of baseball cards or Magic or anything like that, it might say you might get the foil card one in every 5 packs, and you can through experience you probably remember you can open one pack and get the foil card, or you could open 50 packs and not get one. Okay, so probability is never a guarantee. It's just a long run average. That's the important part of probability. All right, another term here, an experiment. So an experiment is a planned operation carried out under controlled conditions. So, rolling a fair die, flipping a fair coin, things like that. That's an experiment. And if the result is not predetermined, then the experiment is said to be a chance experiment. Okay? So again, this rolling a dice and all that. We don't know what the outcome's gonna be. Of course, number 4, outcome. The result of an experiment. Outcome, what comes out of the experiment. If you flip a coin, you could get the outcome of getting heads or the outcome of getting tails. All right, number 5, sample space. This one's pretty important. Sample space of an experiment is the set of all possible outcomes. So again, if you flip a fair coin, then the only 2 outcomes are either heads or tails, right? So this would be the sample space of flipping a fair coin. And the capital S with the equal sign and the curly brackets, that represents the sample space. Again, sample space is all possible outcomes of an experiment. Okay, there's a couple different ways. I just showed you one here to represent a sample space. We can just list all the possible outcomes. We can create tree diagrams, and we can create Venn diagrams. So the one we just did is just listing them. We'll see towards the end of this chapter how to do tree diagrams and Venn diagrams. Like I just told you a minute ago, the uppercase letter S is used to denote sample space. All right, and this is the example I just went over with you. Okay? All right, so again, important sample space, list of all possible outcomes of an experiment. All right. An event. You're going to hear this word quite a bit in probability. So an event is any combination of outcomes. We usually use uppercase letters, capital letters like A and B, or you'll see as we go through this chapter. Again, I'll show you how to use them and when to use them. For example, if the experiment is to flip one fair coin, we might define event A as getting more than one head, or at most one head. All right. So the probability of an event A is written just like this. So this is important. The P parentheses A, it means the probability of event A occurring. So again, that's important. P parentheses A means the probability of event A occurring. Number 7, the probability of any outcome, and I kind of talked about this at the beginning there, is the long-term relative frequency of that outcome. Okay, again, it is not a guarantee. Probability is not a guarantee. All right. Let's see. Probabilities are between 0 and 1. Right. Probability of 0 means the event will never happen. All right. So think of an example as, what is the probability that I wake up tomorrow morning as the Queen of England? It's not going to happen. Right. I'm not female. I'm not British. I'm not royalty. They don't even know I exist. it will not happen. The probability is 0. Probability of 1, or probability equaling 1, means it's a guarantee. It's a 100% guarantee that it's going to happen. What's the probability that the sun comes up tomorrow? All right, now I know, don't worry, I know my physics. I know the sun doesn't rise, but it looks like it to us, right? So what's the probability the sun comes up tomorrow morning? It's 100%. It's going to happen. And if it doesn't, we wouldn't even know about it anyway, right? Probabilities can also be anywhere between 0 and 1. So, if we, for example, if we say the probability of event A is 0.5, that means it's equally likely to either occur or not occur. Right? Again, think of the example of flipping a fair coin. You're either going to get heads or tails. So the probability of heads is 50%, which means half the time, in a long run average anyway, half the time we should get heads and half the time we should not get heads. All right. Number 8, equally likely. I mean, that one's pretty self-explanatory, right? Equally likely events. So equally likely that each outcome of an experiment occurs with equal probability, right? So both heads and tails on a fair coin are equally likely to occur. Another example of equally likely, if you toss a fair 6-sided die, each face, right, they're numbered 1 through 6, is as likely to occur as any other face. We just talked about the fair coin. It's either heads or tails, equally likely. If you randomly guess the answer to a true-false question on an exam, you are equally likely to select a correct answer or an incorrect answer. Right? There's only going to be one answer. It's either true or it's false, 50-50. All right, number 9 here. Probability of an event A. Okay, so that's that P of A again that we talked about. So to calculate the probability of an event A, when all outcomes in the sample space are equally likely, it's pretty easy, just count the number of outcomes for event A and divide by the total number of outcomes in the sample space. Okay, so here's an example right here. If you toss a fair dime and a fair nickel, so we're tossing 2 coins, then there's only 4 possible outcomes. Either both coins end up heads, one's tails, one's heads, or flip it, the other one, the first one's heads, second one's tails, or both could be tails. That's it. There's only 4 possible outcomes if you flip 2 fair coins. All right, so T is tails, H is heads, of course. The sample space has 4 outcomes. So let's say that event A equals getting 1 head. Okay, so there's 2 outcomes that meet that condition. Heads then tails, or tails then heads. Right? Each of those only have 1 T in it, right? I'm sorry, 1 H in it. Okay, so there's only 2 out of the 4 items in the sample space. So there we go, that's what they're showing you here. It's the number of outcomes in the event that you're talking about divided by the number of outcomes in your sample space, S. Okay, so again, if A is getting 1 heads, we know out of the 4, there's 2 ways to get only 1 heads, right? Because HH is 2 heads and TT is 0 heads. And we know that the sample space has 4 items in it. Okay, so 2 out of 4 or 0.5, either way is an acceptable answer. Okay. Let's see, events and probability of events. So here's an example. Let's see, so you roll 1 6-sided die with the numbers 1, 2, 3, 4, 5, 6 on its faces. So this is kind of a standard thing in statistics, especially in this class. If we talk about rolling a die, okay, if I just say roll a die, or if on the homework tests or quizzes, if it says roll a die, we're going to assume, and I know that most teachers always say don't assume, but in this case we're assuming it's a fair 6-sided die. Okay, so make yourself a little note whenever you hear whenever we talk about rolling a fair die, or even just saying rolling a die. In this class, we're talking about a fair 6-sided die. All right, so we're going to define event E as rolling a number that is at least 5. So we got to think of this phrase, at least, right? So at least means the minimum. So if this is our sample space 1 through 6, at least 5 means 5 or more. So event E consists of the numbers 5 and 6 in this case. So we want to find what is the probability of event E occurring. So probability of E, right? So we're going to find the number of outcomes. Oops, there we go. In event E, and we'll divide by number of outcomes in this sample space. Okay, well, we know event E consists of the numbers 5 and 6, so there's 2 outcomes there, and we know there's 6 items in our sample space for a fair die 1, 2, 3, 4, 5, or 6. Now in this class, now I know we're online for this class, but if it was in class, I would say leave the answer unreduced. That's perfectly fine. You'll get full credit. I know you never hear a math teacher say that, except in statistics. But I'm warning you guys, listen on this homework program that we're using, My Open Math. Read the directions carefully. Sometimes it may say leave it unreduced. Sometimes it may say leave a fraction. Sometimes it may say answer in decimal form with a certain number of decimal places rounded. Follow directions, whatever it says on the program. Okay, if you don't follow directions, I don't give full credit. All right. So, if we did reduce this, though, of course, it would be 1/3, right? Okay. Let's see. So if you were to roll the die only a few times, you would not be surprised if your observed results did not match the probability. If you were to roll the die a very large number of times, you would expect that overall 2 out of every 6 times of the rolls would result in an outcome of at least 5. In other words, rolling a 5 or a 6. And like I said before, probability is never a guarantee, so we would not expect that we should get 2 rolls out of just 6 rolls to be a 5 or a 6. The long-term relative frequency of obtaining this result would approach the theoretical probability of 2 out of 6 as the number of repetitions grows larger and larger, and we'll talk about that later. That's called the law of large numbers. Go figure, right? So the more often you repeat an experiment, the closer to its theoretical probability you should be. Again, it's still not a guarantee. All right. An example would be, you could flip a fair coin 10 times and get 10 heads, right? That is definitely possible. But if you flip a coin 10,000 times, chances are you're going to be very close to 50-50. 50% heads, 50% tails. Again, you may not be exactly 50-50, but you should be very, very close. All right. Let's see. So probabilities when outcomes are not equally likely. Okay, so this is now not equally likely. All right, so here's an example. Use the following information to answer the next 6 questions. A jar of 150 jelly beans, so they're telling you, you've got 150 jelly beans. Contains 22 red, 38 yellow, 20 green, 28 purple, 26 blue, and the rest are orange. Okay, so they want us to find the probability of each color. So use letters for our events that make sense, right? So if we want to find the probability of pulling a red jelly bean out of this jar, write it like this. Oops, not like that. Write it like this. Probability of red, R for red. Make life easy on yourself and me, the guy grading it, or in this case now the computer grading it. So again, we just want to find out, well, what's the, how many outcomes are red? Well, there's 22 red out of the total of 150 jelly beans in the jar. It's that easy. Okay? So the rest are going to be very simple here. So the probability of yellow, 38 out of 150. Probability of green, 20 out of 150. And again, you leave these unreduced for my purposes. Again, on the computer program that you're using, My Open Math, read directions carefully to answer correctly. Let's see, so probability of purple is 28 out of 150. Probability of blue is 26 out of 150. And it says then the rest are orange. So the probability, so now this is one way we could do it. There's several ways we could do it. We could just simply subtract, right? Add up all those numerators, add these guys up, and subtract that number from 150, right? Or we could take all the probabilities and subtract. There's multiple ways to do it, and I probably should have done this before, so I don't have to do it with my calculator, but that's okay. A few extra seconds here won't hurt. So I'm going to add up all the different color jelly beans here. So 22 plus 38 plus 20 plus 28 plus 26. So that's 134. So 150 minus 134 is 16. If I got it wrong, just email me. But either way, you get the picture, right? So the probability of an orange, it should be 16 out of 150. And there we go. There's all the probabilities that we need. All right, so it's important to realize that in many situations, the outcomes are not equally likely. So in real life, a lot of times, that's what it's going to be, not equally likely. A coin or die may be unfair or biased, right? You know, people cheat in this world. Go figure, I know. Two math professors in Europe had their statistics students test the Belgian €1 coin and discovered that in 250 trials, a head was obtained 56% of the time and tails 44% of the time. So based on this experiment, again, this doesn't guarantee that all Belgian €1 coins are unfair, as it would be. They're not 50-50. But based on 250 trials, that's a pretty decent sized number. So the data seems to show that the coin is not a fair coin. So if anyone ever has a Belgian €1 coin and says, let's flip for it, well, make sure you pick heads, right? You'll get better probability of winning. So more repetitions would be helpful to draw a more accurate conclusion about such bias. Right? So if they flip the same coin, the Belgian €1 coin, 1,000 times or 5,000 times or something like that, and the numbers still came up 56 and 44%, then you could definitely say these coins are unfair. Okay. Some dice may be biased as well. Okay, you've probably seen TV shows and all that, and people load. It's called a loaded dice. They'll put some weight in somewhere, so it's going to roll certain numbers at a higher probability than other numbers. So some dice may be biased. Look at the dice in a game you have at home. The spots on each face are usually small holes carved out and then painted to make the spots visible. Your dice may or may not be biased. It is possible that the outcomes may be affected by the slight weight differences due to the different numbers of holes in the faces. So in other words, one side has a one little hole drilled in it, and another side has 6 holes drilled in it. So technically speaking, and of course it's going to be an extremely small weight difference, but sometimes it's enough. But with 6 holes drilled out, more material has been removed from the dice on that side than the side with the 1 hole drilled out. All right. Let's see. Your dice may or may not be biased. It's possible that the outcomes may be affected by the slight weight differences due to the different number of holes in the faces. Gambling casinos make a lot of money depending on outcomes from rolling dice, so casino dice are made differently to eliminate bias. Casino dice have flat surfaces. The holes are completely filled with paint having the same density as the material that the dice are made out of, so each face is equally likely to occur. Later we will learn techniques to use to work with probabilities for events that are not equally likely. So here's an example. All right, so the probability that a particular knee surgery is successful is 0.85. Right? So find the probability that 2 knee surgeries are successful. So this one's easy. We're going to get deeper into this kind of stuff later. But what we're trying to find is what's the probability that the first surgery is a success and the second surgery is a success. Well, they told you a successful surgery in this case is 0.85. Now, in probability, so this is the weird thing about statistics and probability. In your previous math classes, think of what the word and meant to do, what operation. And meant add, right? 2 and 3 is 5. But we're in statistics now, or now specifically probability. So now the word and means multiply. So that's important. And I am going to repeat that later. You'll see when we talk about the words and or. Okay. So in this case, and means multiply, and there's conditions that we'll talk about later when to make sure we multiply. But for now, think of the word and means multiply. So success is 0.85, and so we multiply another 0.85. Or you could write 0.85 squared, right? That means multiply by itself. And like I said, for my purposes, you're welcome to leave your answers just like this, unreduced, uncalculated. But on the homework program, again, make sure that you read directions carefully. Answer the way they want it to be answered. All right. And again, this is what I was talking about. So here, A or B event, A and B events. So these words and or. So an outcome is in the event A or B. This is a definition. This is important. An outcome is in the event A or B if the outcome is in A or is in B or is in both A and B. So that's a definition. Okay? So an outcome is in the or statement A and B, A or B, if the outcome is in A or B or both A and B. All right? So in this case, what they're telling us, for example, set A is 1, 2, 3, 4, 5. Set B is 4, 5, 6, 7, 8. All right? So A or B. Read the definition. It's in A or B or both A and B. In other words, we're going to take every number from both of these sets and just not repeat them. Okay, so we have 1, 2, 3, 4, 5. Part B also has 6, 7, and 8. So there you go. A or B, in this case, is 1, 2, 3, 4, 5, 6, 7, 8. Notice, of course, 4 and 5 are not listed twice because the outcome of 4 in set A is still the same outcome of 4 in set B. Okay, so we don't need to repeat that. Let's see, an outcome. So now this is a new one here. So an outcome is in the event A and B if the outcome is in both A and B at the same time. So that's important. They have to be in both A and B at the same time. For example, at A and B, so let's say this is set A right here. Yep. There we go. Set A is 1, 2, 3, 4, 5. Again, set B is 4, 5, 6, 7, 8. So A and B, think of the intersection, right? The intersection of two streets. If you're standing in the middle of the intersection, well, it's not a very good idea, but if you're standing in the middle of the intersection, you're on both streets at the same time. That's the physical overlap of the two streets. Think of it like that. Physically, where do these two sets overlap? They both have 4 and 5 in common. Okay? So that's the way to remember. The and is also known as intersection. Right? Again, think of the intersection of two streets. It's where the two streets physically overlap. It's what they have in common. So there we go. So A and B is just 4 and 5. Okay, another term here, the complement of event A. Well, I'll go through it and I'll show you definitely an easier way to memorize what the word complement means in statistics. So the complement of event A. The complement of event A is denoted A prime. So it's got like a little apostrophe on it. Okay, that's A prime. So A prime consists of all outcomes that are not in set A. Okay, not in set A. All right, so let's try this out. So notice, so basically what's going to happen is this is an important equation right here. The probability of event A plus the probability of event A complement equals 100%. Okay, so let's say event A is rolling a 1 on a fair six-sided die. So that probability would be 1 out of 6, right? So the complement means the opposite of that. In other words, the probability of not rolling a 1, which means 2, 3, 4, 5, 6, which means a 5 out of 6 chance of not rolling a 1. So 1 out of 6 plus 5 out of 6 is 6 out of 6, which is 1. Okay? So here's another example. So let S, remember S always represents our sample space, all possible outcomes. So S is 1, 2, 3, 4, 5, 6. Set A, event A is 1, 2, 3, 4. So a complement, so things that are not in set A, but in the sample space are now 5 and 6. Okay? And like the example I just showed you, so the probability of event A is 4 out of 6, because there's 4 items out of the 6 in the sample space. The probability of A prime, a complement, is 2 out of 6, because there's 2 items out of the 6 in the sample space. And if you add 4 out of 6 plus 2 out of 6, you get 6 out of 6, which is 1. Okay? That's important stuff right there. All right, and then we have conditional probability. So again, let the words help you define them. Conditional, there's conditions, there's prerequisites, right? Something has to happen first. Right, it's like, when you get your college acceptances or your university acceptances, usually they're conditional acceptance, right? We accept you on the condition that you pass all your classes or at least get a certain GPA or something like that. There's conditions. All right, so the conditional probability of A, given that B has already occurred, is written just like this. This is the notation, okay? So again, that means the probability of event A occurring, given that, so that little bar means given that B has already occurred. That's important. You're going to want to write that down. The probability of event A occurring, given that event B has already occurred. Okay, and there it is written down there for you. Conditional reduces the sample space. So we calculate the probability of A from the reduced sample space B. We're going to do some examples later on in the notes that'll make that more clear to you. All right, so let's see. Let's check these out. Let's see. So example, suppose we toss one fair six-sided die. The sample space, 1, 2, 3, 4, 5, 6. So let A equals, we get either a 2 or a 3. Let B faces even, so that's 2, 4, or 6. So we want to calculate the probability of event A occurring given that B already occurred. In other words, we want to find what's the probability that we get a 2 or a 3 given that we get a 2, 4, or 6. Okay, so I'm going to show you this in a minute. So we count the number of outcomes, 2 or 3 in the reduced sample space, 2, 4, 6. Then we divide that by that number of outcomes, B rather than S. So that's going to be 1 out of 3. After we learn more rules, we'll have a formula to calculate conditional probability. So don't worry about conditional just yet. A little bit further into this chapter, we'll get into it. All right. All right, so 3.2, section 3.2, independent and mutually exclusive events. All right, so again, we're going to kind of go over this conditional probability that we just talked about. So this is a Venn diagram, and we'll talk more about these later as well. But a Venn diagram, the Venn diagram below is a way to represent the basic idea of probability, such as sample space, an event, A and B, A or B, and conditional probability. So it's just a visual way to represent all this probability stuff we've been talking about. The rectangle represents the sample space, so that's this guy, the big old rectangle. That's every possible outcome. And the area of it represents the probability to get the events in the sample space, which is 100% or 1, right? Remember, sample space represents all possible outcomes. So the circles represent events. So that circle A means, event A, whatever that may be. Circle B represents event B, whatever that may be. And notice this like football shape in the middle, the overlap of the two circles. This is the intersection, overlap. It's what the two events A and B have in common. Notice this notation right here, right? It's like an upside down U. That means and, right? Or intersect means the same thing. So if you see that symbol there, which you will see, I'm going to use it quite often in this class. That means and, or the intersection of two events. All right, let's see. So the area they share represents probability of A and B, like I just showed you there, and the total enclosed by the circles represents probability of A or B. So what they're saying is, because remember, or means it's either in A, in B, or both at the same time. Okay, so if we were to color in all of this, that would represent A or B. Okay? All right. If we have equally likely outcomes in the rectangle or circles, then to find probabilities, we just count the outcomes, just like we've done before. And we'll do some Venn diagram stuff in a little bit. So this one's important. This is a formula you need to make sure you know. The formula to find conditional probability can be made more intuitive by the use of this Venn diagram. So here is the equation for conditional probability. So let's say the probability of event A given B, all right, is the probability of A and B divided by the probability of B. Now, I'm going to show you an easy way to remember this. So the numerator is always the and statement of both of these guys, whatever two letters they use. Probability of E given F, whatever, it doesn't matter. You use the and statement for the numerator. For the denominator, you're always going to take the second statement right there and put it there, the probability of that. Okay? So the second thing, the given that statement, always goes in the denominator for this equation. Okay? Very important. Make sure you know this. Let's see. Note that the probability of B given A is the area of B that is in the A, or how much of B given that we're already in A. And notice if we're in circle A, then the part of B that is in A is how much A and B have in common. Thus the numerator formula, the and statement. Okay? All right, so that's important. This is also important right here. Independent events. This is an important definition. You're going to see it quite often. Two events, A and B, are independent if one of them occurs, they're independent if when one occurs, it will not change the probability of the other one occurring. Okay? Whether you pass or fail a test does not change the probability that the person next to you passes or fails the test. As long as everyone's being honest, of course, and not cheating. But that would be independent, right? Whether you pass or fail doesn't change whether other people pass or fail. All right. Two events are independent if the following are true. All right. So these are important as well. So let's think about this. What is it saying here? So the probability of A given B equals the probability of A. So what we're saying is event B occurred. It happened. Whatever it is, it happened. But it did not change the probability of A, because the answer is still just the probability of A. Okay? And we can switch it around. Of course, the probability of B given that A has already occurred, well, A has occurred. But it has not changed the probability of B occurring. All right? We can use another equation too, because again, these equations are just based on what do we need to find, just like back in algebra, right? And you're going to see, I'm going to do several problems with you guys today. Basically what's going to happen is you have to decide which equation to use for probability, and you're going to plug in what's given by the problem and solve for the unknown. Very easy. Okay? All right, and the probability of A and B equals the probability of A times the probability of B, as long as we have independent events. That's important. So if they ask you for an and probability, and they tell you, or at least somehow you know you have independent events where one occurs, it won't change the probability of the other, then the answer is simply take the probability of A, multiply by the probability of B. Okay, so all three of these guys are important. Make sure you know those. So let's see. For example, the outcomes of two rolls of a fair die are independent events. The outcome of the first roll does not change the probability of the outcome of the second roll. To show two events are independent, you only have to show one of the above conditions. All right, so either this one or this one or this one. If any of those three equations end up being true, then you know for a fact you have independent events. If two events are not independent, right? So not independent, the opposite of independent is dependent. One depends on the other. So when one event occurs, for dependent, when one event occurs, it will change the probability of the other event occurring. Okay? All right, so some more terms here. When we take samples in this class, well, we'll talk about taking samples. There's two different ways we can do it. It's called with replacement and without replacement. Again, pretty much self-explanatory, but of course we're going to talk about them here. So if you sample with replacement, if each member of a population is replaced after it's picked, then that member has a possibility of being chosen more than once, right? That's called sampling with replacement. You pick an item or a person or whatever, you pick something out of the group and you record what you got and you put it back in and you pick something again and record what you got. All right? That's with replacement, replacing it back in the group to possibly be chosen again. When sampling is done with replacement, events are considered to be independent. Meaning that the result of the first pick will not change probabilities for the second pick because everything's back in the pile, right? So all the probabilities go back to the beginning. Now we also have without replacement. So this is another good one to know. Of course, both of these you got to understand. When sampling is done without replacement, each member of a population may be chosen only once, right? So, if you pick a card out of a 52 card deck, and you don't put it back in when you choose your second card out of that deck, there's no way you're going to possibly get that same first card you got. You kept it out of the group. Okay? So in this case, probabilities are affected by whatever happens on the first thing you choose. So these events are considered to be dependent or not independent. Same thing. All right. So here's some examples. So sampling with replacement. So suppose you pick 3 cards with replacement out of a 52 card deck. The first card you pick out of the 52 cards is the Queen of Spades. You put this card back, reshuffle the cards, and pick a second card from the 52 card deck, and now it's the 10 of Clubs. You put the card back, reshuffle, and pick a third card. This time it's the Queen of Spades again. All right. Your picks are Queen of Spades, 10 of Clubs, and Queen of Spades. You got the Queen of Spades twice. And we picked each card from the 52 card deck. So this is with replacement. This is just an example showing it's possible to pick an item one time, and when you put it back, it's possible to pick it again. Okay. All right. So here is an example of sampling without replacement. So suppose you pick 3 cards without replacement. First card is the King of Hearts. You put it back, or you put it aside. I'm sorry. Pick the second card from now 51 cards remaining, and it's the 3 of Diamonds. Put that card aside. Pick a third card. Now there's only 50 cards left in the deck, so you can kind of already see how and why the probabilities are changing when you pick a card and don't replace it. All right. All right. So the key phrase here is we cannot pick the same card twice without replacement. All right. All right, so here's another example. Now, this is a chart that shows a 52 card standard 52 card deck of playing cards. You do not need to memorize the properties of of a 52 card deck. It doesn't hurt to understand them a little bit, but you don't have to memorize it. But just so you know, so the pictures on the cards here, those are called the suits. Okay? And these suits, we have clubs, spades, hearts, and diamonds. All right? And you can see half the cards are black, half the cards are red in the 52 card deck. These cards here, the jacks, queens, and kings, are what are known as face cards, because quite literally they have faces on them, people's faces, right? Okay. So there you go. Just some general information about a 52 card deck. Again, you don't need to memorize this, but it's good to know that kind of stuff. All right, so let's look at some of these examples here. So here's some outcomes. All right, so let's look at number one here. So QS means queen of spades. The rest of them mean the one of diamonds, one of clubs, and the queen of diamonds. So if we look, we got 4 different cards, right? No repeats. So is that outcome possible without replacement? In other words, if we pick the queen of spades out, can we get the one of diamonds? Yes, we can. And keep that out, you can still get the one of clubs. Keep that out, you can still get the queen of diamonds. So without replacement, this outcome is possible. What about with replacement? Well, yeah. With replacement, we can get any card again. So this is also possible. Okay. Next example, number 2 here. King of hearts, 7 diamonds, 6 of diamonds, king of hearts. So notice we got a repeat here. So can you get a repeated card without replacement? So if we pick the king of hearts, take it out of the deck, there's no way we're going to pick it again. So this is not possible without replacement. But it is possible with replacement. Sorry, I just don't want to keep writing possible. Okay. Let's see. Third example here, queen of spades, 7 of diamonds, 6 of diamonds, king of spades. No repeats, right? So possible for both. Okay. All right. So let's keep going here. All right. Mutually exclusive events. This is an important definition. Mutually exclusive. A and B are mutually exclusive events if they cannot occur at the same time. This means that A and B do not share any outcomes, so the probability of event A and B occurring at the same time is 0. Mutually exclusive events are like, the probability of flipping a coin, one single fair coin, there's no possible way to get both heads and tails on one flip, right? That cannot happen. The probability is 0. Okay. Here's another example for mutually exclusive. Suppose the sample space is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Event A is 1, 2, 3, 4, 5. Event B is 4, 5, 6, 7, 8. And event C is 7, 9. Okay? So A and B, right, if we find the overlap, and means overlap in this case, the intersection, A and B have both 4 and 5 in common. So the probability of A and B is 2 out of the 10 items in the sample space. So it's not 0. Therefore, A and B are not mutually exclusive. In other words, there is overlap between set A and set B. Okay, if there's overlap, we do not have mutually exclusive events. Let's see, so A and C do not have any numbers in common. So let's look at A and C. So here's A, 1, 2, 3, 4, 5, and C is 7 and 9. No repeated events, no overlap. Okay, so the probability of getting something that's in both A and C at the same time is 0. It's not possible. So A and C are mutually exclusive. So if it is not known, which in the problems they'll give you information so that you know whether they're mutually exclusive or not. If it's not known whether A and B are mutually exclusive, assume they are not until you can show otherwise. All right, so here's a bunch of good examples with probabilities here. All right, so we're going to flip 2 fair coins. So this is an experiment. So the sample space is, and we talked about this before, right? You could get heads then heads, heads then tails, tails then heads, or tails then tails. So those are the outcomes, and they are equally likely. Right? So in other words, the probability of any one of these 4 different things occurring is 1 out of 4. Okay? All right, so we're going to define some events. So let A be the event of getting at most 1 tail. So we got to talk about that little phrase there, at most. So think about what that means. Is that a greater than or a less than statement? At most, it has the word most, but it's actually a less than statement. Think about if I say, I'm going to give you at most $5, right? That means that's the maximum. 5 is the maximum, but I'm cheap, so I'll probably only give you $1. Actually, I'm probably going to give you nothing, but at most means a maximum, in other words, a less than statement. Okay, so at most 1 tail actually means either one tail or 0 tail. Okay, at most 1 means either 1 or 0. So in event B, we're going to say that's the event of getting all tails. So in this case, we can see that's TT, right? Okay. All right, so let's describe set A. So at most 1 tail. So here we're going to say A equals, this is how we write sets out, like I showed you before. A equals, and put the curly brackets there. So look at the sample space. Which ones have either no tails or only 1 tail? Well, HH has no tails, HT has 1, and TH has 1. Okay, TT, of course, has 2 tails. That's more than 1. All right, so there we go. That's what set A looks like. Event B was the event of getting all tails. So that one's easy. So B equals tails, tails. Okay. All right, number 3 here. It says find the probability of event A. So again, we look at event A. A has 3 items in it out of the 4 items in the sample space up above. That's it. That's how easy that question is, right? Really no work to show. So let's see, probability of event B, same general concept. B only has 1 item in it, tails, tails. So 1 item out of the 4 in the sample space. And there we go. So on a test or quiz, this is really all you need to show, although, again, I keep forgetting, but you guys will be taking your test online, but that's okay. If it was on paper, this is the amount of work I would expect to see for full credit. All right, let's keep on going here. So now they're saying event D is the event of getting more than 1 tail. So more than 1 tail means not 1, right? More than 1 means 2 in this case. So set D is tails, tails. Okay. So what's the probability of event D? Well, there's only 1 tails, tails out of the 4 items in the sample space. So 1 out of 4. And of course, make sure you put your equal signs in appropriately. All right, keep on moving here. Event E is the event of getting a head on the first roll. So again, we're looking at the sample space. So heads on the first roll. So which of them has an H as the first letter? Well, HH and HT, right? So there's 2 items in there. So event E is heads, heads, or heads then tails. Okay, and again, the probability of E, well, there's 2 events in E, or 2 outcomes in E, out of the 4 possible outcomes in the sample space. Nice and easy, right? Okay, let's keep going here. Let event F be the event of getting at least 1 tail in 2 flips. So at least 1 means 1 or more, right? So again, at least means that number or more. All right, so event F would be, we look at the sample space, which items have either one tail or both tails, right? So that's heads, tails, tails, heads, and of course, tails, tails. All right, so the probability of this event F, well, there's 3 items in F out of 4 in the sample space, 3/4. All right, nice and easy, right? If only it stayed that easy. All right, so section 3.3, 2 basic rules of probability. First one, the multiplication rule, and these are each just extremely important. You've got to know these, okay? If you don't know these, this is going to end up being pretty rough. So if A and B are 2 events defined on a sample space, then the probability of A and B equals the probability of B times the probability of A given B. So if you notice, this is just, if we divide both sides by probability of B, this is just the equation for the conditional. Okay, so you've seen this equation before. It's just manipulated with algebra. If A and B, so that's an important equation to know. This is another important equation. If A and B are independent, remember what independence means. If one event occurs, it will not change the probability of the other event occurring. Okay, and we talked about these up above, but good to know. It's nice to have them all in one place now. The probability of B given that A occurred is equal just to the probability of B, because A occurred and it didn't change B's probability. And the probability of A and B, if we have independent events, again, that's important. If we have independent events, then the AND statement simply means multiply the 2 probabilities together. So probability of A times the probability of B. All right, next rule we have is what's called the addition rule. So if A and B are defined on a sample space, then the OR statement, finding the probability of A or B occurring, this is what we do. We take the probability of A, add the probability of B, subtract the probability of A and B. In other words, subtract the overlap. Okay, and let me show you why. I'm going to use a Venn diagram here to illustrate why this equation is true. So here's a very ugly Venn diagram. 2 circles. This is event A. This is event B. Okay. So you know what? I gotta kind of fix this. Hey. There we go. There we go. Okay. All right. So let's look at this a little closer. All right. So we've got this Venn diagram. Event A is the circle on the left. Event B is the circle on the right. So this is what I'm going to do. I'm going to draw some little dots in here. Okay, so this is what I'm going to ask. Let's see, how many dots are inside circle A? So this is circle A. Just count 1, 2, 3, 4, 5, right? Okay, so 5 dots inside circle A. How many dots are in circle B? Right? 6 of them, right? Okay. Add those together, we get 11, correct? 6 plus 5 is 11. However, count how many dots, blue dots are here. There's 9. So how did we get 11 if there's actually only 9 dots on this Venn diagram? The problem is, in this 5 and in this 6, we're double counting those 2 in the middle, the overlap, the AND statement, the intersection. All right, so that's why we ended up with 11 when there's really only 9 dots on the Venn diagram. That's why we have to subtract the overlap. Okay, so that's important. Make sure you know this equation as well, very important. All right, if A and B are mutually exclusive, in other words, if there's no overlap, then the probability of A and B equals 0, and the probability of A or B. So Remember I told you the upside down U means and, the regular U means or. Okay? That's important, very important stuff to know. So if we have mutually exclusive events, in other words, events with no overlap, then the or statement simply becomes probability of A plus probability of B. We don't need to subtract the overlap because the overlap is 0. Okay, so let's do an example using all these equations here. Let's see, Juan is trying to choose where to go on vacation. His choices are A, New Zealand, and B, Alaska. But he can only afford one vacation. So that's an important statement right there. He can only afford one vacation. So we're going to give some probabilities here. So the probability of A is 0.6. The probability of B is 0.35. So let's use our newfound knowledge of with the equations and the rules and all that stuff, and let's figure these things out. So what is the probability? So number one here, probability of A and B. So in other words, what's the probability he goes to New Zealand and Alaska? Well, he just said he can only afford one. So that probability is 0. Number 2, find the probability of A or B. So we've got to think, do we have mutually exclusive? So this is an or statement. We have to ask, do we have mutually exclusive events? Well, again, you cannot go to New Zealand and Alaska at the exact same time. They're way too far apart, right? So they are mutually exclusive. They're not outcomes that can happen at the same time. So we just found out right up above here, when we have mutually exclusive events, when there's no overlap, then we simply add the two probabilities together. Right, in this case, they told us the probability of A is 0.6 and the probability of B is 0.35. Add those together, you get 0.95. So based on this information, there's a 95% chance he's going on vacation. All right. Number 3 here. Find the probability of A or B. And now this one has a little C up there. We haven't seen that before. But what that means is complement. Okay, it's the same as what we saw before, probability of A or B with a little prime mark on it. The prime and the C mean exactly the same thing. They are the complement of each other. So complement means basically the opposite. It's not really the opposite, but it's an easy way to remember it. Okay, and the funny way, I was going to tell you before, but I'll tell you now. The funny way to remember complement, that it means the opposite, is think, back to your days in high school. If someone gave you a compliment, what did they really mean? They meant the opposite, right? It's a joke, I know. It's just a funny way to remember this, right? So there we go. Complement means the opposite of. Again, it doesn't really mean opposite. It's just an easy, kind of funny way to remember the equation. The equation here is we take 1 minus the probability of A or B. Okay? And that's based on that equation before. We said the probability of the event plus the probability of its own complement always equals 1, right? Okay, so we know, we just found in number 2 here, we found this, didn't we? Yeah, we did. So that answer is, so we do 1 minus 0.95, which is 0.05. So in other words, in words, this would mean the probability that he does not go to New Zealand or Alaska is 5%, 0.05. All right. Okay, we keep going here. All right, another example here. So a student goes to the library. Let event B equal the student checks out a book, and D equals the student checks out a DVD. And this is kind of a smart thing to do, right? Use the letters that make sense. It makes it easier on the brain. If we say A is book and B is DVD, then it could get kind of confusing or mixed up in your head. All right, so use letters that make sense for the events. All right, so they're telling us the probability of B is 0.4, probability of D is 0.3, probability of D given that B has occurred is 0.5. Okay, so we're going to use our knowledge of all the equations that we have up above that we've learned recently, and figure this out. Again, just think it's just like algebra. You're going to use the equations, fill in what you know, and use algebra to figure out what you don't know. Okay? All right, so here we go. Probability of B and D. Well, look what we've got. We've got conditional, and we've got the probability of B here. So if you remember the equation, so I'm going to write it off to the side here. Probability of D given B is the probability of A. I'm going to use the symbol here. A and B over, remember we take the second thing here, the given that statement, and that goes on the bottom, probability of B. Well, we're looking for A and B. So if we multiply both sides by probability of B, we get this equation. And we've had this equation up above, but we would get the probability of D given B times the probability of B. And we have both of those. Look, right there and there. So we have this information. That's awesome. Plug and chug, right? Plug these in. And so D given B is 0.5 times the probability of B is 0.4. Okay, and again, these were given right here and right here. So if you multiply those together, you get 0.2, and there you go. So there's about a 20% probability of B and D. So in other words, the student checks out both a book and a DVD at the same time. All right, number 2 here. Find the probability of B or D. All right. So the or statement, if we're just going to add the two probabilities together, B and D, these have to be mutually exclusive. In other words, there's no outcome in common. But we just found out you can get a book and a DVD at the same time. So there is overlap. So not mutually exclusive events. So which means we have to use the equation we learned up there. Probability of B plus the probability of D minus the overlap. The probability of B and D. We just found B and D right up above in number 1, right? Okay, so we look up here, we use the information that we're given. Probability of B is 0.4, probability of D is 0.3, and we just calculated B and D at 0.2. So add and subtract all this up, you get 0.5. So there's about a 50% chance that a person gets either a book or a DVD. Okay, so let's move on here. Another example. And we're doing a lot of examples because you'll see, especially with this example that we're going to do right now, the stuff can start getting quite a bit complicated. The hardest part is just figuring out which equation to use at what time. All right. So here we go. Studies show that about 1 woman in 7, so about 14.3%, who live to be 90 will develop breast cancer. Suppose that of those women who develop breast cancer, a test is negative 2% of the time. So here we go. Negative test 2% of the time. Also suppose that in the general population of women, the test for breast cancer is negative about 85% of the time. So let event B equals a woman gets breast cancer, and let N equal tests negative. Suppose we choose one woman selected at random. All right, so then we're going to answer all these questions based on what we just got here. So what's the probability that the woman develops breast cancer, right? So it said right up there, probability of event B occurring is 0.143. That's that right there, right? When we do these probabilities, of course, as you can tell how I'm writing them, we're going to convert percentages to decimals or fractions, whichever you prefer working with, but not percents. Okay. Second part, what's the probability a woman tests negative? So the probability of event N, well, they told us that is 2%. Or I'm sorry, 85%, right? So 0.85. Right, and we're just pulling that information right out of the question that they gave us. All right, so part B here, given that the woman has breast cancer, what is the probability that she tests negative? Okay, all right. let's think about that. We've got to convert that into a statement we have an equation for, or at least knowledge of. In other words, what they're saying is, what's the probability that they test negative given that they have breast cancer? In other words, the test failed, right? The test didn't work. It said right up there, suppose in the general population of women, the test for breast cancer is, where did it go? Suppose that of those women who develop breast cancer, the test is negative 2% of the time, right? So that's a given, that's a conditional statement. So that's 0.02. Remember, be very, very careful with percentages less than 10. Remember, you've got to put a 0 in there. Don't put 0.2, because that's 20%. All right, part C. What's the probability the woman has breast cancer and test negative? Okay, so there's an and statement. So probability of breast cancer and test negative. All right, so again, let's look at what we've got. We've got conditional, and we've got the probability of B again. So we can use that equation right there. All right. Okay, so let's see. This is going to be probability of N given B times the probability of B, right? Because we always use the second statement there for the other probability. Okay, we know that both of these we can just simply plug in. So N given B we just found out is 0.02, and the probability of B from part A here is 0.143. And if you punch that into a calculator, you will get 0.0029. Okay? All right, part D here. What's the probability that the woman has breast cancer or test negative? This is an or statement, right? So we have to ask, are these mutually exclusive events? Right? And we found out before that they're not, right? Or, by the information we have, they're not, because the probability of N given B is not equal to the probability of B. The probability of N. Right? That was one of the little equations we found before. So these are not mutually exclusive. Not independent. So what we have for the or statement, we have the probability of breast cancer or, so I'm using the U symbol for or, test negative. And that's going to be the probability of B plus the probability of N minus the overlap. Probability of B and N. All right, and we have all this information here, so let's plug in. So let's see, B is 0.143, probability of N is 0.85, and from part C here we just calculated the AND statement. B and N is 0.0029. So let's see, if you plug in, let's see, sorry, I lost my place here. BNN. All right, and so you can calculate that. Let's see, I didn't pre-calculate it, but we can do that. Let's see, we got 0.143 plus 0.85 minus 0.029. We get 0.9901. There we go. So a hair over 99. Let's see. So now we've got a couple of questions here. We've kind of already answered this, but we'll be able to write them out now. So, are having breast cancer and testing negative, are those independent events? Right? We said a minute ago they're not. No, they're not independent, since those equations we found. Probability of N given B is not equal, so we cross out the little equal sign, that means not equal to the probability of N. And just look at the information we have. N given B is 0.02, N is 0.85. Those are definitely not equal, so these are not independent events. All right. Part F here, are having breast cancer and testing negative mutually exclusive? right? If they're mutually exclusive, the probability of the and statement equals 0. But we just calculated from part C, so this will be no, they're not mutually exclusive, since probability of, let's see, B and N is not equal to 0. Okay? So there we go. All right, next section here, contingency tables. All right, contingency table provides a way of portraying data that can facilitate calculating probabilities. The table helps in determining conditional probabilities quite easily. The table displays sample values in relation to two different variables that may be dependent or contingent on one another. So this is a contingency table. It's basically like a table of data. Suppose a study of speeding violations and drivers' use of cell phones produced the following fictional data. So they made this up just for these problems here. All right, so they give you a table like this. Now what you're going to have to do is you're going to have to find all the totals, right? But that's pretty easy. We're just adding, okay? So if we add straight across here, we get 305. We're just adding. Add these two up, we get 450. And if we add straight down these two columns, we get 70 and 685. Okay, so that's what you're going to do. You're going to fill in all the totals. And what you're going to do is we're going to add the row totals and the column totals, and you need to make sure they add to the same number. In this case, they do. They both add to 755. Okay, again, that's important. That bottom right corner must be the sum of both the row totals and the column totals. Okay, so now that we have this, we can answer some questions. So A, find the probability that the driver is a cell phone user. All right, so we just look at the data here. How many total people use a cell phone while driving? Well, right here. Uses a cell phone while driving? There's 305 people out of this group. All right, so the answer is 305 out of the 755 people that they surveyed. And that's it. That's all the work you need to show. Well, there's really no work shown, but that's all you have to do for these types of problems. And again, don't waste your time. Don't bother reducing unless the homework program tells you. Okay? All right, part B. Find the probability the driver had no violation in the last year. So no violation, we look here, well here, right here, no speeding violation in the last year. A total of 685 out of the 755 people surveyed. All right, part C. Find the probability the driver had no violation and was a cell phone user. So remember what we talked about, the and statement. And is like two streets, Newport and Chapman. The overlap, the intersection, all right, is what they have in common. So let's check that out on the chart we have up here. So let's see, no violation, that's this column, and was a cell phone user, that's this row here. Where do they physically overlap? They overlap at 280. So 280 out of the 755. Nice and easy, right? Okay, so and means overlap when we're doing these well, for all of them, but especially when you're doing these contingency tables. Find where the row and the column overlap, and that's the top, the number, and your fraction, the numerator. All right, part D. Find the probability the driver is a cell phone user or driver had no violation in the last year. All right, so so what we have to look at is are these mutually exclusive, right? So cell phone user, where is it? So this is a cell phone, these are the cell phone user, and no violation. Well, we actually just figured out in part C, there is overlap. It's an or statement with overlap. So we have to use the bigger equation for the or statement here with overlap. So that's the probability they're a cell phone user plus the probability that they have no violation minus the probability of cell and no violation. Sorry, I ran out of room there. And we just plug in what we know. All right, probability of a cell phone user. And the nice thing is, if you look at parts A, B, and C, that's all three pieces we need for part D. And that's going to happen from time to time. All right, so probability they're a cell phone user, that's 305 out of 755, plus probability of no violation, we found that was 685 out of 755, minus the overlap, which we found in part C, minus 280 over 755. So if you punch all that in or calculate that, you should get 710 out of 755. And there we go. All right. All right, part E. Find the probability the driver is a cell phone user given that, so this is a conditional, given that the driver had a violation in the last year. Okay, so let's see, this is the probability they're a cell phone user given that they had a violation. Okay, so we'll use the equation we learned for conditional, given that statement. It's the probability of cell phone and violation divided by, and remember we use the second one for the denominator here, probability of violation. All right, so what we're going to look at to do these, we're going to find the probability of cell phone and violation. So we look at the table, and again means the overlap. So here's violation, here's cell phone. It overlaps at 25, right? And then we need the number of items or number of people who had violations. So right here, speeding violation in the last year, 70 people. That's it. That's as easy as these problems are. Okay? 25 out of 70 in this case. And again, no need to reduce unless the homework program tells you to reduce. All right. Let's see, part F here. Now what they want is, so what's the probability they had no violation given that they're not a cell phone user? Okay. Again, we'll use the same equation, right? So this is probability of no violation and no cell phone divided by the second, right? So the second one here is no cell phone. So probability of no cell phone. So again, we look on the table up there. So let's see, no violation and no cell phone overlap at 405. And means overlap. So 405 and divided by, so the number of items for no cell phone is right there. Oh, sorry, right there. Does not use a cell phone, is 450. And there you go. Done deal. Okay, make sure you practice these types of problems. These are definitely good test and quiz type questions. Okay, so some more stuff here. Tree diagrams and Venn diagrams. So I said we'd talk about these later, and here we are. So a tree diagram is a special type of graph used to determine the outcomes of an experiment. It consists of branches, right? Of course, that's why we call it a tree diagram, that are labeled with either frequencies or probabilities. Tree diagrams can make some probability problems easier to visualize and solve. The following examples illustrate how to use a tree diagram. All right, so here's an example. In an urn, there's two balls, one red and one blue. So we're going to draw two balls one at a time with replacement. Okay, so remember that means we pick one ball, record what color we got, put it back in, draw again. The tree diagram using frequencies that shows all the possible outcomes follows, right? So the first draw, you can either get a blue or a red, right? So that's the first draw. The second draw, so let's say you pulled a blue one out the first time, you put it back in, you draw again, you can either get a blue or a red the second time. Same thing for the red. If you pulled a red the first time, right, there's two possible outcomes for the second draw, either blue or red. Okay? Alright, so that's a tree diagram. Alright, number 2 here says list all the outcomes. So what we're going to do is we're going to follow the branches. Okay, if we go this way, first we had a blue, then a blue. Okay, so these are the outcomes. Blue, then blue. If we follow blue, then red, right? And red, then blue. And red, then red. Right, and there we go. Those are all the possible outcomes of this tree diagram. Okay. Here's another example for a tree diagram. All right, so if there were more than just 2 balls in the urn, the tree branches could get kind of crazy. All right. So we simplify the process by having a branch represent multiple branches. In an urn, there's 11 balls this time. 3 are red, 8 are blue. Okay, we're going to draw 2 balls one at a time with replacement. So we pick one, record the color, put it back in, pick again, record the color. The tree diagram using frequencies that show all possible outcomes follows. So we're using this tree diagram here. So I did it for you because it was kind of tedious to write it all out. But part A says list the 24 BR outcomes. In other words, first draw was a blue, second draw was a red. And they're telling you right here there's 24 different ways that can happen. So that's what they're saying. So B1 means blue ball number 1, R1 means red ball number 1, B4 blue ball number 4, red ball number 1, etc. So these are the 24 different ways. So each of these are all different outcomes. Okay, and if you look, there's 24 total. Okay, so what we're going to do here, we're going to use this tree diagram to calculate some probabilities. All right, so let's calculate the probability of red, then red. Okay, so what this is, it's going to be, so the probability of pulling a red on the first draw. 3 reds out of 11 balls, right? 3 out of 11. Right. Now, what we can look at this as an and statement. Probability of a red and a red. Okay, these are going to be independent events because we're using with replacement. We put the ball back, the probabilities all start all over again as the same. Okay, so it's an and statement with independent events, we multiply. So if we put the red ball back in, the second time we draw, we still have a 3 out of 11 probability. Okay, so if we multiply that, that's 9 over 121. So real quick review, when you're multiplying fractions, multiply across the top and across the bottom separately. Okay? All right. All right, let's see. Using the tree diagram, part C here, calculate probability of red then blue or blue then red. So we're going to use the same kind of basic thing here, but or, right, we're looking at independent events. So it's or, right? So it's or with independent events. So we're just going to simply add probabilities together. So in other words, we're going to find the probability of red then blue plus the probability of blue then red. We're going to use the same logic we used up here in part B to do each individual probability. So the probability of a red first and a blue second with replacement. So there's, again, 3 reds out of the 11 total balls. And we multiply. And there are 8 blue out of the 11. Okay, so that's the first one. Plus, now we need to find the probability of a blue first, then a red. We'll just switch the order. Blue, there's 8 out of 11 balls. and there's 3 out of 11 for the red. Okay, I don't know why those first ones all look like 6s. I'll fix that. Hey, what is going on here? Problem with the iPad. Hold on 1 second here. Okay, let's see if that works. Nope. There we go. That fixed it. All right, let's fix this. 11, 11, 11. There we go. Okay, so there we go. If you feel like it, you can calculate this all out, and you should get 48 over 121. All right, and there's your probability. All right, part D. Using the tree diagram, calculate the probability we get red on the first draw and B on the second draw. All right, so red on the first, blue on the second. So we've already done these, right? It's the same thing we've been doing. So that's the same as saying probability of red and blue. So red, there's 3 out of 11, and blue, there's 8 out of 11. And again, multiply across the top, across the bottom. That's 24 out of 121. All right, part E. Using the tree diagram, calculate the probability of red on the second draw, given that B is the first draw. So we're trying to find probability of red given blue. Blue has already been chosen on the first draw. So what this is going to be is probability of the AND statement. So red on second draw and blue on the first draw, divided by the second statement, so probability of blue on the first draw. Okay, so let's look at this. So red on second, blue on first. So what that is, so red on the second draw, because we're doing with replacement, so the probability of getting a red is 3 out of 11. I'm sorry. So let's see. Yeah, there's three reds. So 3 reds out of 11. And blue, there's 8 blues out of 11. Divided by probability of blue on the first is 8 out of 11. So notice the 8 out of 11s reduce away, and your final answer is 3 out of 11. All right, using the tree diagram, calculate the probability of blue and blue. All right, so blue first, blue second. Again, it's with replacement, so the probabilities don't change. So probability of blue and blue is simply we're going to do, so probability of a blue ball is 8 out of 11. And on the second one, since we replace it, still 8 out of 11. So 64 out of 121. All right, part G, using the tree diagram, calculate the probability that blue on the second draw given red on the first. Okay. So this equation would be the probability of blue on second and red on first draw divided by, we use the given that statement, so probability of red on the first draw All right, so blue on the second, there are 8 out of 11 blue. And red on the first, there's 3 out of 11 reds, divided by. And probability of red on the first, which is 3 out of 11. And again, you notice these two fractions reduce away. Final answer, 8 out of 11. Okay, so I know those are a little bit complicated, but definitely make sure you practice these. Okay. All right, moving on. Venn diagrams, we've already used these a bit, but just another quick recap here. Suppose an experiment has the outcomes 1, 2, 3, all the way to 12, right? Where each outcome has an equal chance of occurring. So they're going to say set A is 1, 2, 3, 4, 5, 6. Event B is 6, 7, 8, 9. Okay? So A and B, remember A and B, and means the overlap, the intersection. If we look at set A and set B, they both have a 6 in common. Right? A or B means just take both sets and put them together as one. Just don't repeat any numbers. Okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So to draw these out into a Venn diagram, so remember the big rectangle means the sample space, all the possible outcomes, which they told us is 1 through 12. Event A has 1 through 6 in it, so there they go. Event B has 6, 7, 8, 9 in it, but they told us to make sure we know that the overlap of A and B has 6 in it. All right, so that's how we're drawing this Venn diagram. And the only numbers we didn't use are 10, 11, and 12, so they go in what's called the universal, the rest. They're not in A or B, they're outside. Okay? All right, nice and fun, right? Here's another example for Venn diagrams. Suppose an experiment has outcomes black, white, red, orange, yellow, green, blue, and purple, where each outcome has an equal chance of occurring. So let event C be green, blue, and purple. Event P is red, yellow, blue. So C and P, the overlap of those two sets is blue. C or P, remember or means take all the items in both of the two events and just put them in, just don't repeat any. So let's draw a Venn diagram representing this situation. So very same thing we did before. So the rectangle represents the sample space, so it's all the colors that they listed have to be inside there. They said inside C is green, purple, and blue. Inside P is blue, red, and yellow, and we said the overlap was blue. Okay, and the only ones that weren't in C or P are black, white, and orange. So those go out there. All right, so just some basics there on Venn diagrams. Okay, let's do another example here. What's the probability of getting 5 different cards out of a 52 card deck? In this case, we're going to say without replacement. Okay, without replacement. In other words, we pick a card, we look at it, we don't put it back. Pick another card, etc. Right? All right. But in this case, it's even a little bit more complicated. It says no 2, 3, or 4 cards of the same value, the same number. In other words, if we get a 2 of clubs, we don't want to get another 2 at all. So we have to eliminate all of those. Let me show you what I mean. So the probability of this thing happening, probability of getting 5 different cards. So let's see, we're going to pick one card. Probability of picking any card in this 52 card deck with nothing taken out of it is 52 out of 52, right? It's 100%. You're going to get a card. No problem. All right, so that's the first one. So we're going to multiply here because we're saying we get one card on the first draw and a different card on the second draw and a different card on the third draw, etc. So we're multiplying. So now let's say, it doesn't matter. Let's say we got a 2 on the first draw. All right. So there's one less card to choose from now because we're doing this without replacement. We already picked a 2. So now there's only 51 cards to choose from. But we don't want to choose another 2, so we have to eliminate all 4 2s. In other words, now there's 48 cards to choose from out of 51 because we already chose a 2. Okay? I know it's a little complicated. All right, but we're doing this 5 times. Now let's say, it doesn't matter. Let's say we got a 4 on the second draw there. So now we don't want any 4s. So we picked a second card out of the deck now and did not replace it. So now there's only 50 cards left in the deck to choose from. But we don't want 2s or 4s because we want different cards. Okay, so now we're going to subtract another 4. Now there's only 44 cards with numbers we have not chosen yet, or values. And we keep using the same logic here. We need to do this 5 times. We've already done it 3. So we already chose a card. So now there's only 49 cards left to choose from. And doesn't matter. Let's say we got a jack, right? So we don't want jacks anymore. So we subtract another 4. Now there's only 40 cards to choose from. And we keep going. So, and now we want another card we didn't have. So now there's 48 cards left. We've already picked 4 cards out of the deck. There's only 48 left. And again, doesn't matter what you choose. Let's say we got an 8 on that one, so we subtract another 4. So now there's only 36 out of 48 cards, so we don't repeat a value. Okay? For my purposes, this answer would be fine, but if you really wanted to, you could use a calculator. It would multiply out to 2,112 out of 4165. Or if you punch that in and get a decimal, it's 0.5071. So just short of 51% chance of picking 5 different cards out of a standard 52 card deck and not getting a repeat of the number or letter on the card. Okay, hopefully that made sense. All right, I think one last example. Yes, all right, one last example here. Okay, so what is the probability of out of 10 people in a room that nobody has the same birthday in that room? So there's 4 choices right there, but let's do the calculation here. All right, so the probability nobody shares a birthday. So it's going to be kind of similar to the logic we just used on the cards here. So what we're going to say is, well, for the first person out of the 10, it doesn't matter what their birthday is. There's 365 choices for the 365 days out of the year. Okay, but we want them to not have the same birthday. So 365 out of 365. And for the second person, right, we don't want them to have the same birthday, so now there's 364 days to choose from out of 365. And we keep doing this. We'll do this 10 times, right? So the next person, 363. And we keep going. Again, what we would do, because this will take forever to write out, we'd keep writing these out, and then the last one would end up being, there's only 356 choices out of 365. So if you punch all this into a calculator, you will get answer A. So it kind of sounds high, doesn't it? It's a little bit surprising maybe. So if there's 10 people in a room, the probability that nobody has the same birthday out of those 10 people is actually a little over 88%. Kind of surprising, right? Again, that doesn't mean it's a guarantee. It just means there's a high probability that out of 10 people in a room, nobody shares a birthday. All right. And there you go. That's the end of that chapter. As you can see, this chapter is a little rough. I definitely recommend going through this lecture